Good morning, sir.
Good morning, madam.
Yes. Shall we start?
Yes, I think we shall start.
Okay, continue, Priya. And just start. I'll give the. You just start the session. I'll give the introduction and everything. Okay. Or should I directly start?
I will give the introduction.
Okay.
Yeah. Good morning, all of you. Welcome, one and all, for the day 4, session 4 of research opportunities in environmental engineering. And today we have a speaker with us, Dr. Kelkar. So I request Dr. Vidula Sohni, HOD, Bharati Vidyapit, Department of Civil Engineering, to please introduce our today's speaker.
Okay. Thank you, Priya. Good morning, all of you. I am Dr. Vidula Sohni, Head of the Civil Engineering Department, Bharati Vidyapit Deemed University College of Engineering, Pune, and one of the conveners of this workshop. We have gathered here for the faculty development program on research opportunities in environmental engineering. It is a 6 days faculty development program which is jointly organized by Bharati Vidyapit Deemed University College of Engineering, Pune, and SB Patil College of Engineering, Indapur. For this particular FDP, we are basically focusing on protecting the environment by covering the various aspects of environment. So accordingly, we will be covering the various aspects related to environment such as water quality research, air pollution control, waste and wastewater management, climate change, etc. Out of this, right from the first day, we have already covered a few aspects. On the first day, Dr. Ajay Raghava has covered the climate change. On the second day, Dr. Kamyotra has covered challenges in air quality management. Dr. Third day, we have that is yesterday we have covered the good economy in waste management, and today we have with us Dr. Uday Kelkar, who will be covering research in water and wastewater treatment. So I welcome Dr. Uday Kelkar as a chief guest, Dr. Praveen Nemade, who is the principal, SB Patil College of Engineering, Dr. M.R. Gidde, who is one of the convener of this workshop, all the faculty members from the Bharati Vidyapit College of Engineering, all the faculty members from the SB Patil College of Engineering, and all the participants who have given us an overwhelming response for this faculty development program. Welcome, sir. Today's chief guest is Dr. Uday Kelkar. I will introduce him. Dr. Uday Kelkar has more than 30 years of experience in the field of environmental engineering. He holds a graduate degree, that is BE in civil engineering from College of Engineering, Pune, and masters and doctors in civil engineering, environmental engineering from Virginia, USA. Over these years, Dr. Kelkar has served in various capacities. Presently, he is the Managing Director of NJS Engineering India, a wholly owned subsidiary of NJS Company Limited, Japan. He has worked on a number of design and engineering projects and studies in water and sanitation sectors in USA, Middle East, Sri Lanka, Vietnam, Cambodia, and India. His specific experience includes advanced treatment processes, including nutrient removal, membrane biology, bioreactors, membrane tertiary treatment processes, advanced oxidation, disinfection with ozone and UV, seawater and brackish water desalination, recycling and reuse of wastewater for non-potable and indirect potable use, and water quality modeling. Dr. Kelkar has more than 150 technical papers and presentations to his credit and has received number of awards, including Hall of Fame Award as one of the 50 most influential people in the Indian water industry. Dr. Kelkar holds professional engineering license from state of Michigan and is a board certified environmental engineer from American Academy of Environmental Engineers. He is an active member of various professional organizations, including AWWA and WEF. On this occasion, I once again welcome Dr. Uday Kelkar. We had a good opportunity to interact with him on one of the projects related to Pune Municipal Corporation on JICA. So once again, I welcome you, Dr. Kelkar, sir, and request you to start your presentation. Thank you.
Thank you so much, Sohini madam, for the introduction of our today's speaker. Now I request Dr. Uday Kelkar, sir, to please start your session.
Mic.
Mike.
Now, can you hear me?
Yes.
Okay. I said good morning to everybody. It's quite an honor to be part of it. And looks like I can only see a couple of faces, obviously, because so many participants are there. I hope all of you are in good health and being safe in this pandemic, which has really thrown a monkey wrench into all the processes and your day-to-day operations. This pandemic is especially challenging for all of us working in the field of environmental engineering, both as a drinking water as well as a wastewater situation, because microbial contamination and microbial systems are very dangerous in the processes that you need to look at it. The most urgent and most utmost is you need to have unhealthy water that is able to drink, and also you need to have a wastewater that will be appropriately treated and processed and so forth. With the advent of information being provided that you need to wash your hands more and use a soap more and so forth, the possibility of more water to be generated and more water to be disinfected is going to be high alert. Also, there has been a data recently that there is an RNA available of the COVID-19 in the wastewater. So wastewater could be substantially used as an early indicator of the wastewater that flows into your wastewater treatment plant. And foremost is going to be very challenging for the operators, especially at 3 or 4 locations where there is a lot of aerosols that comes into picture for primary clarification, for secondary clarification, and also at the upfront of the plant. So the operators will have to be very extra careful in considering the operation of the plant because of the way the COVID get transmitted from one end to another. And lastly, there will be a lot of discussions and research and systems will be developed and applied upon when a lot of people in the past and also in the future will talk about use of recycled water for various applications, including direct or indirect potable and industrial use. So that also will have a lot of significance in terms of what type of disinfections, what level of disinfection, what level of contact time, and what level of dosage requirement are considered not only for COVID-19 virus, but also any other future viruses that might turn up. What I would do if I can share my slides, I have a lot of slides I've tried to put together. I don't know how many of them I will go through one by one or how many I have to skip because of the time constraint. And I also had no idea how many of the staff members and also how many of the attendees are at different levels. So if you find some of the slides that are not higher ended, they're just smaller, just skip them in your mind and we'll go more into the systems. Madam, I'm going to share the slide presentation if I can.
Yes, sir. So you can share it.
Okay, let's see where it is.
So there is a share option on the toolbar which you can see.
I have it.
Yeah.
I'm just looking at it. Can you able to see the slides?
Yes, sir.
Okay, great. Thank you. Works well. Essentially, I want to focus on 2 sides, water first and then wastewater. and then focus on different aspects of water, the design, the issues that can be lead to variety of processes, and then what's out there for wastewater treatment systems. What needs to look at it, how we as an engineer and as well as an interest in research have come up with some of the projects that we have and what are the future tasks that we need to consider. As I said earlier, some of the slides that you might see have come from textbook or have come from my interactions. So if you feel that those slides are not really relevant, we'll skip it and we'll go more into detail. What you see on the first screen is basically a water reservoir on the left-hand side corner, then obviously a cascade aerator, a treatment plant. On the right-hand side, you see a design of a plant. I will talk about that in a soon, but that's quite an interesting project that we did, where the idea of doing research together with the contractor was really beneficial. The slide on the bottom side, which is basically a brand new plant that we are building as an engineer, designer, and I think Sue is constructing this plant. This is going to be the largest plant in India, or that might be Southeast Asia, which is 564,000 meter cube per day. This plant is in Delhi, and this will have what you want in wastewater engineering, everything in there, right from grid removal systems, proper aerated grids, then primary, secondary, biological treatment, and then nitrification, denitrification, phosphorus removal, sludge digestion, electrical generation, power, UV, disinfection, sludge creating for fertilizer, as well as drying aids and so forth. So once this plan gets completed, people would love to come, especially academicians can bring their students and so forth to see this plant, because then you will have the entire McCafferty sitting there at a 564,000 meter cube per day plant in Delhi, another 3-4 years. On the right side is just a simple photograph of a DAF plant in the process. Let's talk about water treatment. And some of the slides, as I said, I'm going to skip it because they are generic, and it just gives me an aid to the process flow in the system. Essentially, in the summary, or the systems, what we look for is the source. You have river, lake, artificial pond, aquifer, and I've noted there a GW, a groundwater, and then ASR. This is going to be a prominent, particularly where water resources are going to be constrained. And there's a lot of research needs to be happen in ASR, which is nothing but an aquifer storage and recovery, where you use a confined aquifer and do the analysis of geotechnical assessment, do the analysis of water quality assessment, do the modeling, and store the water and pump it out whenever it's needed. Obviously, storage could be a simple storage or a lake to draw the water, and I'll explain what I meant by that. Disinfection pre and post, depending upon the water quality needs. Nowadays, UV radiation has picked up much more significantly because of the availability of UV lamps that are better in operation, lower in cost, easy to manage as compared to any other disinfectant or oxidants that are named below under chemical. You also have membrane filters, which in last 20 years has panned up much more significantly because of the cost slowdown, manufacturing processes have improved, technological systems have improved, and the material science for membranes, including PVDF and PVCs and PV sulfones, have created much more faster and easily accessible membrane filters. In the science chemical, chlorine is good old horse, which is everybody likes to use, easy to handle, easy to operate, but has got limitations. And as we move into newer and newer regulations, say, for example, trihalomethane formation, oxidation of total organic carbon using chlorine, sudden accidental leak of chlorine, and so forth. For example, certain places in the US, there is a risk management condition where you need to move from chlorine to liquid chlorine because of gaseous chlorine, accidental spillage. This is because in the older times, your treatment plants used to be away from the society, away from the city. Now, because of the development, because of the growth within the city, most of the water and wastewater treatment plants are now coming within the city limits or very close proximity to the population and so forth. Then you have ozone, you have chlorine dioxide, you have iodine. A lot of these have pluses and minuses based on how they operate, cost-wise, design-wise, raw water quality-wise, what affects what. For example, if you want to look at ozone as one of the strong oxidant and disinfectant, certainly it is. But it has an issue with respect to bromate. If you have a high bromate concentration coming from your groundwater or coming from your reservoir, coming from geomorphological conditions, then bromate has an issue with ozone because it will form bromide. Bromide will give you color and it will be a pinkish, brownish mixture water. If there is an iodine, same issue will happen. So we'll talk about that, how to look at the disinfection and decay on SIP. In filtration, good old granule media filtration, which is being used in most of the countries. It's a rapid sand filters. It has got a lot of research inputs still ongoing, including particle retention, particle-particle interaction, how the amount of filter time can be increased given, because ultimately the longer the filter time you have, the lower the energy consumption and maximum is the production of water. So you're trying to optimize how your filter operation will be done, whether filter can be done dual media or single medium, that is just a sand and a gravel, or you have multimedia. You'll have an anthracite, or you have GAC, or you have a granular media combination. Depending upon, again, your own water quality, you could do research around, you could develop research approaches for a variety of applications of this. I'll give you one classic example. If you have ozone coming up or thinking of using ozone in your system, it may be worthwhile to look at it if you have organic carbon coming into your raw water, which will be to a degree, whether it's a smaller or larger percentage, maybe 1 milligram per liter or maybe 5 milligram per liter sometimes. Most of the organics that you see into the natural streams is because of your formation coming from decay of trees, decay of organic material, and humic and fulvic substances. Large molecular weight compounds. If they are being oxidized through chlorine and ozone, then you could do an assessment in the laboratory or at the site that what amount of organics are being chopped, what is the larger molecular weight is happening into a smaller size. You can do it with a simple filtration process. You can have different filters being bought from chemical manufacturers or chemical suppliers, where you can take 1 micron to 0.1 to 0.2 to 0.4 and 0.6 micron and filter the water at different levels to see what level of organic compounds are available, what chain compounds are available, and then essentially consider whether you want to use a GAC mix, that is granular activated carbon filter, along with your sand, and operate this GAC filter as a biological active filter, BAC. Because once you apply a biological active filter and you have a very strong oxidant up front, it will chop off the molecular weights into a smaller size, which are very well amenable to the microbes sitting inside your GAC inside the filters. And that will actually help reduce your biological as well as organic level, and which will reduce eventually the formation of disinfection byproducts, which are basically DBPs for your THMs and haloacetic acids and so forth. I'm actually going to go through you all these details. A lot of people know about this or may have done research, but I put a generic thought process in this. The next one, I'm going to skip to the source and just go to the membranes. You have ultrafiltration, micro, nano, and obviously reverse osmosis, depending upon the water quality, depending upon the nature of the treatment you want, depending upon where you want to apply it, depending upon what size of area you are available, and whether you want to have a retrofittation, non-retrofittation, brand new plant, and so forth, can then basically look at it. Chemical coagulation, precipitation, complexation is also there. Adsorption is also there. For example, you could have different material tested. Instead of activated carbon, you can have a bone char, you can have naturally developed activated carbon processes or naturally developed adsorbents. For example, some sands or some type of mixture of materials can have a different adsorption properties and may actually work out better for your particular area or your particular design and the systems and so forth. I'm going to skip this because this is a standard slide. Here's what I wanted to show it to you is basically how this thought process of doing research might be able to help. On the left-hand side, it is a direct application coming from a river through a canal going to a treatment plant. On the right-hand side and the bottom one are basically a reservoir. Now, when we did this large-scale project in Bangalore, the original plant on the left-hand side was, on the right-hand side and the bottom, that they were feeding their water through this particular reservoir, which was getting fed by the canal on the left-hand side. And because of that, there was a good amount of residence time being created within this particular reservoir. And at the intake location, if I can take my mouse and say this is the intake location for a large 500 mld size plant or 500,000 meter cube per day size plant, the actual water quality was actually coming much more better or superior into the intake going into the treatment plant. What happened to that is because of reduction in their operations, reduction in their chemical usages, reduction in disinfection, and so forth. What was actually happening in this particular reservoir, which apparently they had this land available and they started using it as a toning reservoir, that particular attenuation was given to the incoming turbidity, incoming TOC, or total organic carbon, and any other contaminants. In the next step, when the new project started, they wanted to go directly to the canal rather than going into the lake that they had created. What turned out to be, because of this particular assessment, they had to do the research on this particular water quality and substantially change the treatment processes, substantially change the treatment units and the operation and maintenance of the processes, because what was earlier is no longer going to be there. So that's a change in water quality. And the next one they had to do is to dredge out, because over the years the sediment started becoming a little bit anaerobic and started releasing the nitrogen and phosphorus within the upper laying body, giving the water enough nutrients, giving the water enough food for microbial activity as well as hyacinth, any other activity to happen. And hyacinth started growing substantially over the system and also created an organic carbon increase in the water. So they had to do an aeration within that particular lake. So this all happened based on the research that we did in the systems. You could also do these researches. The systems that needs to be looked at it is the carbon, nitrogen, and carbon phosphorus transforms, leachings from the sediments, and aeration of the sediments, and so forth. Here's the data that we did, relation between the COD nutrients and the data from the study that we did for one of the plants, total nitrogen, total phosphorus, and limiting nutrient needed to be found out based on the treatment process. You still can continue to look at it. There is a lot of work has been done on limnology, and they still continue to do it. And based on now the relationship between total phosphorus and carbon, total phosphorus and total organic carbon, molecular size reduction and molecular size changes within the nitrogen and carbon, and so forth. Every lake, every system is different. So one size may not be able to fit all. What you can get is an idea to look at it, where to search, but your solution will be unique for your own processes. Here's the research that we did from bottom of the sediment on one of our projects. I'm fortunate that I do get involved in technical design engineering, even at this stage, and also on some research with universities that we jointly do to get. So I guess it keeps my brain cells active so that in case I'm retired, I can go and do other teaching and anything else. That's just a side note. So this is what can also be looked at for limnological side of the way of considering what needs to be research side of water and augmentation systems. Here's the lake stratification data. One of the project that I worked on in Virginia was a very unique in Virginia Beach area, where there is a lot of lakes supplying water to the city of Virginia Beach and city of Norfolk, Lake Prince and Lake Charles, and all these lakes were getting stratified over the time during the summer and the winter period. And basically, they were trying to leach manganese and iron into upper water that was changing the water quality coming to the water plant. And we had to do this. We had to do analyze and speciation of combination between iron and manganese and also TOC and so forth. So this is when finally an aeration was conducted, and designed to be so that during the stratification, if you apply a certain amount of air into the process, it will provide an oxidation to the hyperlimnatic and limnatic water bars and basically not stratify the lake and essentially increase the water quality in the process. There are different types of aerators. This is one what we used in Hyderabad, in Lake Hussain Sagar, for developing these, reducing the stratification and also reducing the applied slug of nitrogen and phosphorus coming from the sediments, which were found to be highly anaerobic in nature. This is what we looked at it. For asparagine, essentially an air blows through a pump into a system, has a mixer at the bottom, which mixes it and then it flows through. I think in Gujarat and also Baroda and Ahmedabad, they have used this for a similar type of lake restoration. There's another one sometimes people have done in Nainital and other places that you can put aeration system through a linkage of pipe and simple air conduits at the bottom or membranes at the bottom and to have an aeration. Is another one that I looked at it during one of my work in US and also now doing outside. It's a simple mechanical aeration, doesn't really put air bubbles or doesn't really put into it. It's quite an interesting space. Essentially, it just brings the water up and down and changes from your limnatic condition to non-limnatic, changes the stratification into normal air mixing. It doesn't disturb your flows or your water levels at all. And it has got an idea that it can go up and down in the height. So if the limnatic conditions are in the case of hyperlimnian and lower side of the waters are deeper, you can essentially increase the length of it if you look at it on the left-hand side. They have used it, and we actually went and visited this in Lake Warragamba Dam in Australia, where if you look at it, these were solar powered. The same solar B was on the solar powered system, where it says the solar power was providing enough energy, less than, I think, 5 kW or 2 kW range pump systems. And essentially what they were having, a lot of water that is coming from non-point source pollution into this particular lake, Warragamba Dam, which is being used as a reservoir for water supply to the city of Sydney. And because of these non-point source pollution, they were seeing algal growth in certain times in blooms, algal blooms during certain times of the summer. And that was creating a lot of problems in the treatment plants downstreams, which were using it for city of Sydney, where if you have the idea, or if you've worked on the plants, you can see that when the algae comes, it has got a long chains species. You need to have an oxidation. Otherwise, if you add a coagulant up front, it will just start winding up into the process and everything will float and will create a messy system. It will never settle down and so forth. So by doing this aeration with the solar B, with the solar activated panels, they were able to reduce considerable amount of algal blooms coming into the plant and save. So this is a process. This is just, I talked about it, your standard conventional plant and so forth. We talked about physical process. This is I'm going to skip some. Can you hear me?
Yes, sir.
Okay, because there was that's the another issue that we have in the speed that we were at. Now I'm getting connected again. I get to redo this. Just now? Hello?
Yes,
Hello?
sir. Yes, sir, you are audible.
Okay, great. So then talking about this, another problem that also do research on, it's called as active research. Active flow. Active flow is a solid contact settlement process. It was kind of unique that if you add a very small particles that will act like a seed sitting into your treatment plant actually reduce the extreme footprint of your sedimentation basin. And we did this pilot first when I was doing in US, and we tried to do it here in India. The cost was substantially higher to begin with. But essentially, it's not a seeding process. So you might remember that at times people used to add some sort of small amount of sand particles, small amount of soil particles to the treatment processes to coagulation. It's exactly what this was, an active fluid given a brand new name and so forth by US Filter at the time. So there's a lot of work needs to be done in what size of the sand you want to use, what side of sedimentation you want to use, because ultimately that sand that gets down into the sludge has to be removed through hydrocyclone. What hydrocyclone speed? So these are all, it's a direct project, but we still need to do a research on things during the design stage, during the process stage. This was the plant I was involved in Tampa Bay, which is a 150 MLD or 150,000 meter cube per day plant. And we engineered, we also work out what level of sedimentation we need to use so we can reduce the footprint and a plant at a higher settling velocity as compared to here is talked about organic carbon additions and combinations thereof. I would like to walk you through membranes. That's what is going to pick up now on a water and a wastewater side. This is generic for water and wastewater processes together. Essentially, you have a physical barrier, whether it's an ultrafiltration or a microfiltration, and which gets rejected. For the ultra and microfiltration, typically for a drinking water side, you can use all the way up to 95%, 98% reject, 98% through 3% or 2% rejection. So your water loss is not significantly higher. It's similar to your water plants up to 5% many times. The size of the pore, it's a 0.1 micron or 0.01 micron, help you to prevent almost all the bacteria and about certain percentage of viruses, because the size limits its physical process. Now, if you look at it, cryptosporidium, which is about 3 micron, giardia, which is about 4.5 micron, and so for any other microbial contaminant, including E. coli and fecal, everybody will get retained on the surface. Especially MS2 coliform, only 30% will get retained. But that's the reason you need a disinfection post so that you can have a and going into a distribution system. What research is happening nowadays in membrane is membrane material, type of membrane pores, what the different types of pressures, because there are pressure membranes where you apply a pressure to the water through a pump, which are going to be pushed through the system and then is created. You have a suction type membrane. Let me see if I have a photograph of that for a second. I don't have that. In a suction type membrane, where you can have water going through the center portion of the material and being or pulled the center portion. So the dirty water is on the outside, the clean water is coming from the center, and they are vacuum based. So their cost is lower, their operative conditions are lower, their systems are differently operated. I'll show you one of the projects that we did. It was quite an interesting project when we used membranes as one of the alternatives for this particular process to look at how the is associated. So we can develop a research group on a particular project type, membrane fouling, how times the membrane is involved, what is the longevity of the membrane surface, membrane material. Typically, you can get about 5 to 7 years of membrane life before backwashing the membrane. And essentially 15 years is the life where the entire membrane is bad, that you need to replace the membrane effectively immediately, because the flux, all the capacity, area through the process membrane, flow through the membrane is reduced substantially. You can't really get those membranes anymore. So that's how I used to look at it. This just gives you information about. There are a lot of membrane manufacturers, known manufacturers out there. The US Filter MJet. Now I think it has become, industry has become too fast in the system. I think this is now taken by DuPont, if I'm not mistaken. Then you have a Mitsubishi, you have glass, you have cooked bronze, you have a flat, you have tubular, a number of them available, and everybody has some pluses and minuses. Excuse me. You can do in the laboratory. There are a lot of materials available to construct your own membrane processes and find in the work system. Now, these are being now available for both water and water. The person that started membrane in the operation for section type was the company called Xenon out of Canada. When I was in the US, I was really fortunate to work with those projects with Xenon, and the company I used to work for called CDM. We did application brain into a van, and at that point, a rookie engineer, didn't know whether they will work or not. Kind of shot down, and I said, no, conventional is better, and now it realized that was the project they given by the government of Ontario under the Special Grant Commission project. Ultimately, it became the manufacturers and researchers through the pioneer on the eventually the GE. Applications out there now, the wastewater sector, reducing the footprint, reducing the processes to be required, and using membrane use and research. A little bit spectrum where we are. This is where puts into the picture. This is where urban is. Urban or your concentration plants are micron size, right up to. You can get off. Please understand, right-hand side, chemical filtration, interaction, in combination. When you to the filter, or then material or the material that you particles interact, they are significant. So it's a physical process. It's a lot of work and still going. Pioneer has been in the field for so many years. Dr. Bob is my colleague into the particle research has happened. The ones on the left hand, the mic, and the ultrafilter nano and the reverse osmosis are all physical processes. They remove one physical on a surface. There's no chemical interaction indirectly. You go into reverse osmosis. Here now you're in the hyperfiltration, ionic level also to reduce some level of lithium and nitrates and nitrites and so on. On what type? Membranes out there in the research and with ion, especially used a lot of develop removal from the these are you want to do HCl hydrogen to the other process. So membrane gas is one of the largest systems manufacturer.
Excuse me, sir.
Ion to be.
Excuse me, sir.
Electric membrane.
We can't hear properly.
Can you hear me? Okay.
Yes, sir. Voice is not clear.
Can you-
Nothing. Excuse me, sir. Hello. Voice is
Yes.
not clear, sir.
Yes, sir. Can you get it now? Clear now? Is it clear?
Not yet,
Yes, sir. Yes,
now
sir. Yes, sir. Now we are clear.
Yes, sir.
There is some disturbance.
I'm getting a motorcycle noise. Now can you hear? Okay. Then second point is your desalination, where you're using systems across on osmotic pressure and reverse
Sir,
osmosis.
please change
Is
the
what
slide
we
also,
see in
please, sir.
RO, but there is a lot of work going on. You see this? Hello? Wow.
Okay, thank you, sir.
Oh, okay. Now I want to talk about desalination, where basically you use reverse osmosis process through RO. If you look at the earlier slide, that's the last is the desalination or RO processes. There's a lot of work now is normal process in your trees. The roots go down and take up water through osmotic pressure going up to your, or example will be your coconut tree, taking water from the bottom of the soil and from the agriculture side, putting it top. The other way around, what we do in membranes is use the reverse pressure so that the salt is remained and the water is cleaned. But it's a very highly less in the sense it is very costly process. It requires high pressure pumps. It requires high osmotic pressure. The rejections are not more than 50%. So new research is happening in terms of what is called as forward osmosis. What we are used to doing nowadays is reverse osmosis, putting a reverse pressure and trying to separate out salt and the water content. Now the FO has been developed, but it is not yet developed to the point that it can be used for a conventional or a drinking water problem. It's being used a little bit to the industrial side. The issue is there where you need to use a chemical, for example, ethylene glycol, or something of that nature where you can separate the salt and the water content. It's still out there to be formed. It is not completely finished in the process. The other point of doing work and research is energy generation within the RO process, because in a seawater desalination, your recovery is only 50% or 45% in actuality. You use a lot of energy. You have a lot of waste energy that is going in. You need to recover that energy so that the substantial energy can be recovered through the process. There's a lot of research happening here. You could also look into that in the systems. Another type of research in terms of use of bathymetry in dispersion and disposal of the reject as well as the intake, because you don't want to put a reject and the intake at the same location or a close proximity to each other. Otherwise, you will be in a circular system where your plant will essentially fail because you're now putting back the dirty water into the intake location and the intake is pulling up into the process. So essentially, you can do mathematical modeling of the systems where your intake will be and where your discharge point will be and how dispersion is going to happen within the seawater. What are the strength of dispersion? What are the waves and the patterns in the area that needs to happen? And we do this in a large scale plant. We're actually doing this are going to do this in one of the largest plant in India. It's going to happen. We're under the design stage right now for Chennai Metro, which is basically a 400 ml product water. So the intake line will be carrying almost 900 ml capacity water desalination to the tune of 30,000 to 35,000 milligrams per liter solids or salt. Here's the same example of why do we need to look at it research and why do you need to look at the thought process. It's interesting. This is one of the data from the plant within the same area, that it has got the influent and outfluent TOC, total organic carbon. And one thing we are suspecting that there is an issue with respect to how TOC is analyzed, whether it's analyzed in actuality using a TOC analyzer, like for example Shimatsu, or it is basically using a COD analysis and converting COD into organic carbon. And that's why you're not seeing any change between the inlet coming of the wastewater and outlet. So this is another way for looking at desalination. Why? Because the amount of contaminants, example for a TOC, total organic carbon, If it is not reduced, then you have a higher fouling characteristics of RO membrane. It may be anybody's membrane. It could be DuPont's membrane. It could be Nitto-Dinko's membrane. But essentially, RO fouling will be a substantial issue. And if RO fouls down effectively faster, then you are increasing the changeover of the RO membranes and then increasing the cost. So this all boils down to cost and operational issues. I just threw this slide just to give you an idea how the cost of the RO systems work. Typically, power is 26%, which is the highest within the process in operation-wise. Construction is only 31%, but it is spread over the number of years of the plant. Pre-treatment and intake and discharge is there. In operation, 15 to 30% is your O&M cost, 35% power, 40% is capex and indirect cost. I'm going to go talk about the third portion on this is disinfection. And obviously, we are interested in looking at disinfecting the water and using it, whether it's a recycled water or a treated wastewater getting discharged into the lake, into the river, or anything else, and so forth. I'm going to start adding in the viruses, coronavirus, or any other viruses that exist or would exist in the future. To look at it is you need to look at the balancing action between the consumer protection, the byproduct, the corrosion, and the enhanced surface system, chemical risk and biological risk. You need to have 99.9% or 99.2%, that is 1 log, 2 log, or 3 log reduction of the microbial contaminant, and while simultaneously reducing the disinfection byproducts, reducing the corrosion content that might happen into your distribution system. Here's an example of your THM, trihalomethane formation potential. You can use coagulation clarification or enhance. One of my PhD work was looking at enhanced coagulation at a different systems and dosages and sizes of the TOC when I was doing the early master's PhD level. Essentially, you could reach an asymptotic condition that no matter how much amount of coagulant or change of systems you do, you're not going to remove any more additional amount of the TOC or the organic carbon that is coming in. So essentially, you have reached the no point of return. You've got to do something different to look at it, how the THM formation can be reduced. There are obviously chlorine being used as a primary, but it adds up trihalomethane formations or trihaloacetic acid formations. If you consider ozone as one of the options, obviously ozone converts not only bromide to bromate, and bromate gives you dibromo chloro, because chlorine is still going to be used as a secondary disinfectant. So you get dibromo chloro, bromochloro, and the combinations thereof. Also, ozone converts acetic acids from your TOC. So you will get haloacetic acid, halo organics, and halo halides. UV is looking at a fair value because then it is not interacting with any of the organic carbon. It's not forming any disinfection byproduct directly. So the combination of either ozone, chloramines, and ozone UV. In India or anywhere else in this Asian countries, we have not participated or used the idea of using chloramine. Chloramines are very good disinfectant, but not as strong as chlorine. So they need to be there so you need to have one particular disinfectant up front, maybe ozone, maybe UV, and then chloramine, because chloramine are longer lasting disinfectants. They're not stronger, but in the distribution system, they are longer lasting. But the issue for them is you have to notify public that you're going to use chloramine. Essentially, you take chlorine and add ammonia to your water before it goes for distribution, because chloramines are known to be notified because those who have a fish pet ownership, that they have fish tanks, they need to be removed through carbon, because chloramine will go through the gills of the fish, as well as create an issue with the water systems, and also has an issue with respect to hospitals that use dialysis for patients. If you don't have an effective notification, then the chloramine can pass through your dialysis and essentially go into the patients. But having said that, taking full precautions, people have used
and have been used chloramines as a secondary disinfectant. They do their research, they do a lot of work ahead of time before switching into chloramines, and have found that rather than chlorine as a longer lasting secondary disinfectant continuing in the distribution system, can essentially be used if we have a proper PR, public relations program, proper advertisement program, and pluses and minuses shown to the people, it becomes beneficial to the systems. Lastly, the chlorine dioxide have been used, but a very minimal usage, less than even 2, 5, 10, 15 plants, because of the way it can't be generated somewhere else and brought. It has to be generated on site, similar to like an ozone, but it has got an issue with respect to disinfection byproduct, especially formation of chlorate and chloride downs when you are operating the plant, and also an issue with respect to the size of the dose that you can use. Maximum about a milligram or to 1.5 milligram can be used. Otherwise, it'll get converted into chlorate, chloride much faster. Secondly, it also has some issue with bromine and iodine in the water. If you have iodine and bromine coming into your raw water, it will terminate iodine, convert it into iodide, and it will give you pink water. It has happened to us when we were operating a plant and didn't notice how much chloride dose we were putting, and accidentally dose went up to 2 milligram per liter, and boom, next day, everything was pink in the system. Let me talk about ozone, because that's what is happening into India nowadays, being picked up, ozone being used for disinfection, taste and odor control, chlorinated byproducts, biological stable water, and reduced. But keep in mind that ozone is not and I want to use the word cheap, but I should use the word cost-effective solution, unless you at most needs it, at most has to have it into the process. And the regulations that are being derived for your particular country, for your particular states, have been getting so stringent that you want to use this type of oxidant upfront.
Hello, sir.
Yes, sir.
Hello,
bola,
sir.
bola,
Is it necessary to change the slide? Because I see that reverse osmosis slide in front of on the screen.
अरे बाप रे. काय करू, बंद करू slide?
No, sir. Sir, you have to share the slides so we can understand what you speak and.
Sir, slides change होता है, sir.
Hello.
There is a delay in slide change that I can see.
Yes. Right,
Right now it is
Sir,
almost
Gide sir, side change होतो sir.
होता है change.
होतो sir.
If you don't have, just tell me, I'll stay longer on that slide. It may be possible that I may be talking to a next slide and you're getting an earlier slide in front of you. That's possible. So just let me know, Ginde sir. I'm here to help.
Okay, sir. Okay, sir. No problem. Thank you.
And now I want to talk about a little bit ozone. Keep in mind, chlorine can be brought as a gaseous, stored it in the cylinders and applied. Chlorine can be brought as a liquid, as hypochlorite. Again, you need to consider what level of hypochlorite you're going to bring. Are you going to bring in 10%, 15% solution, or combinations thereof between 10 to 15% solution? Because the longer the chlorine solution as hypochlorite stays in your silos or in a holding tank, it will create an issue of chlorate-chloride formation and degrade it. And it will change your dosage requirement, because your pumps will be designed or researched based on the size of percentage of the hypochlorite solution that you're going to use. This is especially true for areas where there is a large temperature variation between day and night, especially in the summers. For example, Rajasthan will be classic example, Delhi will be classic example, where you have a very high temperatures in the daytime that could create an issue with respect to chlorate, chloride. Moderate temperature, there is no variation of using chlorine. Anyway, on the oxygen side and on the ozone side, you need to generate it on site. So you need to have a space to put ozone generator. But ozone generator doesn't come with its own usages. I mean, just simple that. You need to use what type of oxygen you're going to use. Are you going to use an air coming from the natural processes through filtration, or are you going to use a liquid oxygen that coming through from tankers? Now, if you want to use air, then you need to have absolute higher purity air that is being going into an ozone generator. a small amount of any droplet of oil can literally blow your ozone generator, because ultimately it's a high power, high arc system where it generates, breaks oxygen into and forms ozone. If you use oxygen, then it's a liquid oxygen, much easier, but you need an evaporator in between so that it will change from a liquid oxygen state to an evaporator state and so forth. These are the things that needs to be evaluated in the system. If a particular client is interested in your area, say, I want to use ozone, you as a faculty, you as a systems can go to them and have a joint research with them, what type of oxygen you want to use, what level of percentage of oxygen. Obviously, vendors will tell you this is what it is, but for your area, for your system, for your client, you need to develop a site-specific conditionalities, what level of backup power, and so forth and so on. Next part on that, once ozone is generated, the next one is how to dissolve it into the water. Without the dissolution, you're not going to get that ozone into water, and it's going to do the trick of disinfecting and oxidizing the water that comes through the process. Again, everything is not free here. When you have an ozone contactor, not all the ozone is going to get dissolved. It's going to get bypassed coming up into your tank. So you need to have an ozone destruct unit used in such a way that it will suck out all the air that's above your tank so that it doesn't affect a human being, because there is a limit. There is an OSHA standard. How many amount of ppm of ozone can a human sustain? If not, it'll have an effect on its brain, if not effect on his muscular systems, and effect on your mucus. So that needs to be looked at it. So ozone looks beautiful, wonderful, lovely, but it has its own things that needs to be looked at it and considered. Here's a slide. I'm just going to show it to you. We can talk later on in detail if somebody wants more analysis and all so forth. You can do your ozone in your percentage area, what type of percent ozone by weight you can get, what amount of energy that can require, and how is the combination that needs to be considered in your system area. Here's a slide showing ozone. Essentially, oxygen going in, you have a high electric discharge into ceramic tubes or ceramic sheets, and then there's an electrode that sparks. And essentially, if you want to see, if you go to a Google and type ozone generator, you will see a typical slide of an ozone, which will see something like this, but it'll also show a blue color arc around these little holes. Essentially, that's the corona formation, or the corona formation due to energy being sent and ozone being generated into the process. Well, as I said, once the ozone is generated, it needs to have a formation of dissolve. How to dissolve that back into? It's got a standard bubble type of dome type of bubble systems. You could design it, something what I was involved in when I was working with CDM Smith. One of my colleague, Chris Schultz, developed what is called as SVIDT, side stream virtual impact venturimeter, which is basically injecting here and then going through the process or so forth. So it was a quite researchy type of work we did jointly with respect to AWARF and CDM Smith and so forth. So there's an opportunity to do that. There's another way to look at it is if you don't have a space, you can use what is called as a virtual static mixers or system static mixers. Essentially, you have a pipe which has got a sleeves inside going left, right, center, like a crisscross, and then you add amount of ozone, liquidized ozone through your flow system into your main pipe, and then it gets mixed for amount of time, say about 9 minutes, 8 minutes, 10 minutes, and then goes to your main distribution system. As I said, ozone could be used as a primary oxidant. Then you need to look at it, what to do with your filtration, or ozone could be used up here post coagulation flocculation. Again, you need to do work on your own water quality, your own area, or specific to the client, because if you have a very high organics here, large molecular weight compound, they're going to use or iron and manganese and any other organics mixture, then they will use a lot of ozone up front. So you will have a lot of ozone dose going from 3 milligram to 5 milligram per liter. But instead of that, if you use a good amount of coagulation processes, enhance coagulation, remove the organics as much as possible, give a better quality water coming onto an ozone plant, then you could reduce your ozone dose to about 1 to 2 milligram per liter, essentially substantially reducing your size of the units, your operative cost, your cost with respect to ozone systems and so forth, and then essentially could use that for downstream and reduce the cost. But there are plants where primary ozone is a must, because it is not necessary that the quality is not that bad, and then you can use ozone as a primary disinfectant. Here's a new process that I've just got message from my colleagues, ex-colleagues from that what they are trying to do. Nowadays, there is a lot of talk within India, maybe the same elsewhere else, that the water quality coming from the treatment plant is absolutely great within the GLR. However, when you do the collection of water within the distribution system, they're seeing a lot of variations in the microbial contaminant concentrations as well as any other byproducts. So what these guys are doing now, using small dosages of ozone to clean up the distribution system. You can do that with flushing, but flushing takes a lot of amount of water to do it, and you're wasting that water. So now this is the way they're looking at, is using ozone in a modular cart, putting on a tractor trailer and going in a distribution system and cleaning up. It's a much better way. There's a lot of data available now. There's an AWWA publication also on this, and could be looked at it in terms of distribution system water quality, because that's what the issue coming up in India nowadays. This is a UV. Essentially, the UV that we look at it as a disinfection, it's about 15, 20 years back, UV started much more fastly coming into distribution or into a disinfection type of processes. Essentially, you have UVA, UVB, UVC, and UV medium type of variation. What we look at it is specific germicidal range, which I've given it here. I'm not sure whether you are able to visible to you or not, but essentially at a 254 nanometers is essentially what you get a maximum germicidal kill, if I can say that's where the kill is the maximum. But I want to clarify that up front, that UV, like any other oxidants, does not kill the microbe, does not kill the species. It just nudes it. It's basically changed its DNA and changes its reproductive capacity. And if the microbe is not able to reproduce, it is not infected, or it cannot infect. That's the premises in this. So basically, UV disinfection cuts down the DNA system or attacks the DNA process where they can't anymore reproduce. If they can't reproduce, then essentially they are non-infectious and can go out. They're still alive, but they're non-infectious. And same is happening, I believe, based on my little research and work and reading, that's what they are doing. A lot of things now using UV for disinfection against the coronavirus into the air system, or coronavirus to be infected on the surfaces, and put a UV lamp across it, and you can get that. Gindesar, I have on time, because I don't know, I'm not following time yet. So it's 11:30. Okay. Hello. Are you guys hearing me?
Hello.
Yeah, can you hear me?
Yeah, sir.
Yes,
Okay.
yes.
The next slide I'm showing is this is the work that I did for my own research work, and also in a lot of plants. There are two types of UV you can use. You can use UV in pipe, or you can use UV in trenches. Depends upon what the application is and how the application is, and space limitations and so forth. Most of the time on a wastewater side, you use UV in the trenches because it's easier, hydraulically controllable. You can pass the UV lamp, you can remove the UV lamp. Accessibility is much easier for an operator and so forth. But for a water plant, you can essentially consider in-pipe system where you can connect the UV to either an individual filter pipeline or a combination of pipeline where everything is coming from a combined different filters and combined water pipe, and you can combine it to that particular aspect. But you need to have given enough space so that there is an operator space involved, because the operator needs to change the UV bulbs which are fitting in here. For example, if you are using a in-pipe system, then you need a space for an operator as a flange, and enough distance between this flange and the flange that is getting connected to your pipe, so that when it removes, it will not have a hurdle of removal. At the bottom, essentially, I've shown how a UV lamp looks like, which is combined process. This is your argon gas, simple tube light. I want to give it to you that as an example. Simple argon gas, and this is your tube light outside. And essentially, then there will be a vessel sitting like this into the process, where that vessel is this particular area, and this is your tube light. So you want to make sure that when the water flows through this particular either high quality treated or drinking water, it goes in close proximity. I think I will do it next slide. That's much better to show there. Okay, there it is. So essentially, if this is your UV bulb, you want to have a dose coming in such a way that all the particles are coming within the UV bulb area, because as the particle is away from the UV and at the end of the surface, you want to make sure that the dose applicability in such a way that all particles will come. And that is the reason when you apply UV, your influent water needs to be very clean, maybe high quality filtered water, maybe double filtered water, so that the particles don't shield or will not shield the microbes that are coming behind it or sitting on top of it, especially viruses. Viruses don't like to float around in the water systems. They like to hang on to somebody like a particle and hide behind it if it's going through a UV process, for example. And then you need to develop a dose and dose response curve for your specific designed water process or wastewater process and so forth. And then this particle needs to, and to increase the contact time, just like a CT, concentration and time for a chemical oxidant, you need to put a vertical flanges going like this, one from here to here, oops, one from bottom to here, so that the water will flow going like this in a sinusoidal way, so that it's closer away from the UV tube. That's how it is designed many times from various manufacturers. There are a lot of manufacturers. There is a Suez, there's a Wadeco AG, there is a Xylem has a UV and so forth. So there's a lot of work has happened. I was fortunate to work in early times when UV was just coming up in drinking water and wastewater matrix. And I was part of the design team where still on Oz and date today, it is the largest UV applied and installed in New York for the city of New York, where they did not want to do water filtration because they have a very high quality, or I would say pristine reservoir area, which is covered very tightly so that no other contaminant comes in. So they wanted to have EPA avoidance of filtration. So they developed a largest UV disinfection as a primary disinfection. So the water just comes in, just does the sedimentation and straight go to UV and then goes for distribution, no filtration. And the largest UV is, I think, about 2.2 billion gallons per day UV. And I'll show you the picture of that. I think I have that. You can have different measurements for UV. There's a lot of research happening on this. How do you do, which type of systems you use, what type of surrogate organisms to use. For example, MS2 coliphage is being used many, many times for viruses. There might be a surrogate that will come for a coronavirus or a SARS-CoV-2 or maybe SOV1 that is already there. And there are other pathogens that we can look at it as a substitute, so that you don't have to actually work with the actual pathogen, but it can give you a similarity reduction or similarity reaction with respect to the dose response curve, with respect to the type of dose, with respect to detention times and so forth. Here is the largest UV, which is about 8.24 billion liters per day. This is a huge project, and this was under construction, and then I come back to India at that time. This was the design engineering. It's the largest UV been operating now very beautifully. If any one of you get a chance to go to US sometime after this whole thing is over, let me know and I can give you the client contacts there to go see the UVs. The plant in Okla, that is the Delhi Jal Board's plant, will have the largest UV in India, which is 564 MLD or 564,000 meter cube per day design plant. Now I've done on water side. On the wastewater side, I will rather skip some of the slides because time-wise, I think I have to finish up by 12 o'clock to have a 12:30 interaction. What I would like to start with this particular slide, this is the crux of the entire unit operation of a wastewater side. The top side, which is suspended growth, attached growth, submerged attached growth, all are ASR processes, aerobic processes, which are basically energy consumers. They need energy, they need aeration, they need oxygen to feed and operate. At the bottom side is your anaerobic processes, which are both suspended as well as attached growth. The classic example of that will be your USB, upflow anaerobic sludge blanket reactors, or your digester, mesophilic, thermophilic, or combinations thereof, so that you can digest the sludge, reduce the organics. The VFS and VFS will be reduced substantially. The organic content substantially reduced, could be used and could be produced energy. So this was a lot of work was initially happening on aerobic, and it is still there. That is still the basics for removal of your nitrogen, removal of your phosphorus, removal of your BOD, removal of your TSS, substantially being still used aerobic. But nowadays, a combination of the treatment processes between the aerobic and anaerobic has started to work very significantly in last 20 odd years or 30 years, because now you want to have energy consumed on one side, but also energy used, because energy is getting very costlier, and you need to start finding out better sources of energy other than your conventional one, and to utilize that for your wastewater plant, because essentially wastewater is required to be treated and processed. I always like to throw this slide in. Tons of processes are available, combinations thereof. You have SBR, you have MBBR, you have waste activated sludge plants, you have MBRs, membrane bioreactors, IFAS, and so forth and so on. I'm not going to go into detail of those. It'll take another couple of hours to do. Technology combinations. This is your standard activated sludge. Primary comes in, you treat with primary, then activated sludge, secondary, sand filter, and then sludge digestion. You can cut all that, just use a primary, and then cut from here to all the way here, and put membrane bioreactor there for this particular portions, and you have whatever you're looking at. And I'll show you another slide down the road, how these changes are happening. These are your conventional rectangular tanks. There are circular tanks. There are combinations of circular and rectangular thereof, and variety of combinations are available. Different layouts, different processes, Oscar type. Everybody comes with something new and names it on that process. On a membrane side, I think the slide was misplaced, but essentially this I was talking about, that you have a dirty water outside. There are a couple of membranes you can have inside out, where the dirty water goes in, clean water comes out, or you have outside in, clean water comes in from the center, and dirty water is from outside. Depending upon what type of application you're using, what type of membrane manufacturer you're going to use, has a different manufacturer, has different configurations. What are the now, as I said, what are the new trends in the environmental regulations and where the research needs lie? Is we have a regulation, nutrients and odor. There will be a lot of issues with respect to BOD incoming, ratio between BOD, COD, ratio between type of COD and type of BOD, particulate, non-particulate combinations, the area between the nutrients, what organic nitrogen is substantially coming, especially in certain parts of the countries or wherever they are, industrial effluents or effluents coming from a small shop. They don't have a combined industrial treatment plants that can come into your wastewater and also unbalance your operation, unbalance your microbial conditions, and basically belly up the plant. That needs to be looked at it. As I said, energy cost to operate, sludge disposal, chemical and freshwater price is increasing. To bring water to the cities, people might be having to go 100 kilometers or 200 kilometers and so forth. Take classical example of Hyderabad, Bangalore, and various other places where they're bringing water, 4-stage pumping, 5-stage pumping, 400-meter head, 100, 200 kilometers distances, and so forth. So need to have that thought process going. To give you an idea on wastewater, why we need to start looking at a new thought process, a new paradigm shift in electrical, because the maximum amount of energy that you utilize, as I said, these are energy consumers in aerobic processes, is above 50%. The rest of it is in the different parts of the area, but that's the largest. And to reduce that, if you have a conventional plant which is only looking for BOD removal and suspended removal, then obviously this percentage will go down to 30%. But if you have an ammonia coming up removal, or your restrictions that you are going to use ammonia as one of the requirement for your discharge standards, or phosphorus as one of your discharge standards, then certainly your aeration will go up to 60% at times. Because I'll give you an example. For a BOD, you have, say, reduction is about 1.2 to 1.5 milligram per liter oxygen per milligram liter of BOD. Whereas in case of nitrogen, to nitrification, denitrification, and ultimately to nitrogen, your requirement of oxygen and then energy is typically about 4.5 to 5 milligram per liter oxygen per milligram liter of nitrogen is going to be consumed. And that's the reason if the nitrification is required, that is nitrate, total nitrogen is your limit in your discharge standards increasingly, then I think you need to look at it different aspects of using this energy or generating this energy from your solids and so forth and so on. Here gives you a slide that I've put it together through, I think Nicholas Applied has done the work. Essentially, different slides, just the primary has a smaller amount of energy requirement, all the way increases as the amount of processes and discharge standards are being changed and the unit operations are being changed. You guys basically get a substantial increase in the energy. Here's a conventional plant, which doesn't require a lot of energy. And I might skip some of these slides so that I can take some time to talk something different, what I wanted to. Here's the secondary where you have a nitrification, denitrification going on and mixture. Here's the tertiary level plant, which is going to be used as faster for formation of gas and so forth. This is the integrated process removal diagram for nutrient removal. This comes from basically the work of a lot of people in US and other places. And the father of all this BNR, or biological nutrient removal, is basically Dr. Bernard, James Bernard of South Africa, and now a consultant to Black & Veatch, US. He's the father. He's basically started looking at BNR and BNR operations and how to do it. And obviously that's why, if you look at it on the right-hand side corner here, it's called UCT. That's where the thought process came up, is the University of Cape Town. And then the University of Cape Town generated different changes of processes and combinations thereof and came up with a different name, but essentially doing the same idea of BNR, or biological nutrient removal. What it does, and the first plant in India was built by us doing the research and also finding out what's required and how to do it, was for the Hussain Sagar Lake plant in 2007 through 2011, 30 MLD or 30,000 meter cube per day and a 20,000 meter cube per day plant, where the plant was discharging into the Hussain Sagar Lake, and the lake was a nitrogen limited. The sediments were creating a lot of nitrogen into the process, and we wanted to limit the nitrogen as well as phosphorus to about 0.5 milligram per liter. Essentially, we could have looked at phosphorus as a chemical coagulant removal, because phosphorus can be easily removed through ferric chloride or alum with a dose differently. But say ferric requires a lower dose, alum requires higher dose, and so on. But it generates a very high amount of solids, and you need to treat the solids later on. So what we thought is, why not we use a biological nutrient removal systems combination so that we can use what I say, this is one of the process, it's called A2O process. Essentially, the word A2O comes with, this is an anaerobic, this is an anoxic, this is an oxic, aerobic process. Anaerobic, you don't have an oxygen at all, devoid of oxygen, zero. Anoxic, you have a small degree of oxygen available. And then aerobic, obviously, this is your nitrification, this is your denitrification at this stage. UCT, as I said, this is just the combination, is how do you pump back the water from one tank to another? Because if you look at this one, you will have nitrate and nitrogen that has been disintegrated, bringing back to here can affect your nitrite, and then can also affect your phosphorus. So that's the reason how you operate it changes the process. But essentially, it's remained. So we did bench scale tests. We did some research on how to operate, and essentially came up with a thought process called JHB, Johannesburg, modified Johannesburg. Essentially, we brought this reactor back to the center, but instead of coming back from here to here, we just put in a small tank up front and allowed it to deaerate this and then bring it into anaerobic zone. So there's no more oxygen left into the process. I need to drink some water. How do you determine is whether there's an oxygen, no oxygen? You just take your meters,
basically oximeters, and just measure oxygen there. And if you have a negative number going there, then there's no oxygen at all. If you have a slight positive, then there's an oxygen, then there's a high oxygen, and you are in aerobic process, and so forth. I'm going to skip some of these slides. As I said, this is what the stoichiometry. So essentially, you need about 4.6 gram of oxygen per gram or milligram. The alkalinity is consumed during nitrification, and you need to have, if your wastewater is very low alkalinity, then it may be required to add up certain amount of alkalinity so that you will not have a acidic water going out. I'm going to skip some of these slides because there's a little bit more detailed. This is denitrification. On the stoichiometry side, you have about 2.9 gram of oxygen removed, 2.5 gram of methanol required, depending upon the reason methanol required there is, again, you got to find your own research ways that whether you are limited in terms of food. Methanol is essentially carbon. You're putting a carbon into the process so that it doesn't deprive of having a carbon in the process and does do a denitrification conversion of NO3 to N, nitrite to N. Let me see. Okay, I want to talk a little bit about this, how you operate your, say there is an existing plant and you wanted to use for a nitrification and denitrification, and you need to create an anoxic zone. Your existing aeration tank can be slightly bifurcated to give you about 1.5 to 2 hours of retention air, and the rest of it operative in terms of nitrification. But what if you want to convert this to a BNR plant, which we did for a 20,000 meter cube per day or 20 MLD plant? Essentially, I'm going to go slide a little bit down. Essentially, what we did is created another zone here that became an anaerobic zone, and then operated it in such a way that the wastewater coming up is reduced, coming into an oxygen system. In a BNR process, what you will always find, it's quite an interesting for a lot of people to see, and suddenly you see a slug of phosphorus coming up. If your wastewater is coming in from left to right, and this is your anaerobic, this is where your phosphorus reduction starts happening or coming out of phosphorus. And that's why invariably, if you do an analysis of influent phosphorus, let's say it is 4 milligram per liter, at the tail end of your anaerobic process, you will see a lot of phosphorus, more than your influent. And suddenly, if you don't have an idea, you'll start jigging, what is happening? Why my phosphorus is increasing? It is because during the anaerobic process, your phosphorus is going to be removed from the cell mass, put it back into the liquid, and that's why if you see this higher. Once it goes into an aerobic process, then the microbes, the bugs will start telling each other, hey guys, I've got enough air. I don't need this phosphorus or PHAB to be used as my electron receptor. Let's grab them, and it'll take up much more faster phosphoric back again into the cell mass, become heavier, and settle down. And that's the reason at the end of aerobic, you will see your curve like this. So don't be surprised. At the end of anaerobic, you will see a high growth or high number of your phosphorus concentration. Just be alarmed that your aerobic process should be sufficient enough to remove that. I'll give you how phosphorus is removed, because many times people don't understand that mechanism. I've tried to do it graphically here. If this is a cell body which has got a phosphorus in here, fatty acids are stored, and this is a PAB or PRB, phosphorus removing bacteria. When it sees there is no oxygen, there is no carbon available, very low carbon is available, no nitrates, nitrites, then it starts taking out this phosphorus out from the body and starts using it to an extent to an electron receptor. And what happens to that is like a charge and discharge batteries. It's here in this case, it is a charged battery with phosphorus. They don't see anything coming, so they want to discharge this battery right over here, use this phosphorus linkage, and then when it goes to aerobic condition from there to here, they see a lot of air, a lot of oxygen available to do metabolism, to activate energy and all. Then they start taking up this phosphorus that was given to them, discharged from their body, and bring it back here, and then essentially store at a heavy. It's like hungry for a phosphorus. They try to pick up a lot of phosphorus that they already released from, and then excess phosphorus gets here, particle becomes heavier and gets settled. That's how a biological phosphorus removal happens. Here's that classic example which I wanted to show is BioP. This energy is using
polyphosphates and PHAB in volatile fatty acids into systems. In anaerobic conditions, this guy is let it out. This guy is being used as an energy and then essentially used for metabolism. Nitrification. These are standard numbers developed over time. So I'm actually not dwelling onto it. I do have a lot of input, but I'm sorry for the time. Change in alkalinity, as I said, nitrification will have about 7 milligram per liter alkalinity as calcium carbonate, and you need to have sufficient alkalinity in your denite going in, because denite will create an alkalinity. So you want to have sufficient coming in so that you don't chew up in the process. Here's a issue with respect to, again, you can do a standardized data and then use data for your own wastewater plant, your own research group, what type of SRT, that sludge retention time, and what type of BOD reduction I can get at a different temperature and different temperature mass or a region thereof. This is from Japan Water Association, Japan Water Works Association, one of the data that we had shared with them. The next thing I want to talk about is how do we optimize power in the process. As I said, there are different treatment processes that are coming up. One is called as the noble nitrogen removal NMOX process. SBR has got a NADEDA process, which is basically nothing but a smaller molecular or smaller group of granulars that act like anaerobic and aerobic within the system and essentially remove. And then high energy MBRs is the process. Here's the third process which is happening latest in last 4 or 5 years is what is called as MABR, which is not an MBR, which is not a membrane bioreactor, but membrane aerated bioreactor. And the reason people are pushing for this now, because it is seen that instead of using the diffusers at the bottom of the sedimentation, at the bottom of the aeration tank, you could now essentially use membranes from some of these manufacturers, Oxychem, Fluence. I think Oxychem is now DuPont. They have bought Oxychem over. Essentially, you use membrane as a fine bubble diffuser, put membrane racks into your sedimentation tanks, so you don't have to have diffusers at the bottom, and you don't have to empty the tank to clean up the diffusers. Essentially, you can lift the membranes up from here and clean up and put it back. But advantages that they are drawing, that there are almost 45 to 50% energy reduction are happening. And based on that reduction, you could see that a very fine bubble is being injected into water, and you're getting a slime growth on these membranes, which is acting like a simultaneously nitrification, denitrification process in the system. Here is another one which also talks about biofilm through an MBBR, that moving bed biological reactor. You have a plastic media of different sizes. You can develop your own, or you can use standard, which is Chaldean. So there are a couple of them now on the board, which has got a different. Essentially, what you're doing here is you're changing the surface area of the microbial attachment and enhancing the surface area of attached growth and essentially enhancing the operation in terms of systems. We use this project concept in a plant in Agra, where Yamuna water, which flows from Delhi to Agra and on and downwards, was contaminated like a wastewater secondary level. The levels of ammonia in the river are still used to be an R, up to 30 to 45 milligrams per liter ammonia, BOD up to 30 to 55 milligrams per liter, phosphorus similarly, and so forth. And they used to use this water as a raw water source and applying chlorine like anything to oxidize completely all these inorganics, the BODs, the ammonia, and so forth. Their literally average chlorine dose was about 60 to 80 milligrams per liter for a disinfection and oxidation. And if you walk into that plant in those times, you could see a watery eyes because the effervescence of chlorine was so high. And the chlorinated water was looking like a yellowish tinted water. What we thought, since there is enough carbon coming into the water, like a secondary level, there is enough ammonia into the water, why can't we use an attached growth process? That means for a water treatment plant, why can't we use as a wastewater upfront treatment and then treated by a membrane as a physical barrier? Would it help? And because it has worked in secondary plants in everywhere in the world in creating tertiary plants, and it did. by God, we did a pilot for 1 year of operations and doing work and so forth, and fed water in different qualities and so forth, and essentially gave this water that was absolutely getting clean. This is the right-hand picture is basically a photo of this plant. Essentially, this is the original plant which was using contaminated Yamuna water. Now this is the only plant that is being used at 144 MLD or 144,000 meter cube per day plant. And it is producing crystal clear water. Ammonia is coming up less than 2. Essentially what we did, we used these plastic media into the water. It acted like a media with a surface. It grew slime growth, I would say slime, but it's not a microbial growth inside and outside. And that acted like an ammonia nitrification and denitrification system, and essentially used that ammonia as a food. They had the carbon, so essentially worked out for ammonia reduction. Nitrification happened and denitrification happened right there, and essentially you could reduce that water. Now the water is absolutely drinkable, and I've been happy to say that we received several awards on this, even from Singapore, SIWW, and also from Government of India, well acknowledged that this was a unique out-of-the-box thinking. So this is another idea of research backgrounds, research thinking to be done and considered in the process. Here's the data for you for a full-scale plant. This is the raw water. This is the finished water. The raw water have total suspended going. BOD, if you look at it, in certain times of the day, it could go to 19, 20, 30 milligram per liter. Ammonia, if you look at it, it could go to 5, 6, 8, 10, 9, sometimes 15. And then essentially you reduce down to way below finished water requirement of the system. Anybody has a time to go to Agra, please do go. This is a plant in Sikandra, just before Agra, about 5-6 kilometers just before Agra on the left-hand side. You could see the plant, and it will be interesting to see how a wastewater being kind of treated like a wastewater first and then water second on. This is a Nereda plant. I don't want to go in detail, but essentially you form a granular type of medium and then essentially operate like a grain balls in the system. The new process that is happening is called Anamox, where if you know that you're going from ammonia to nitrate to nitrite and then back again to nitrogen, this is the process. Requires about 63% issues. Now it is just cutting short, going from here, and then boom, just going to nitrogen. It is going to reduce the cost, and I'll show you here in this next slide. The normal process takes about 4 to 6 kilogram or kilowatt energy per kilogram of nitrogen. The denite takes about 2.5 to 3, and the next Anamox process, the last slide on the bottom slide, is essentially 1 to 1.75. The substantial reduction in energy, i.e. reduction in cost, reduction in footprint, and so forth. These are new research thought processes that are happening. This is again similar to anaerobic sludge issues. This is a UASB mixed with DHS. Same idea like MBBRs. Essentially, it's got a media hanging in the sludge on in the water, and then essentially having nitrification, denitrification combined. There's another one called Organica water, essentially using root to treat the wastewater incoming. But again, you need to have a consistent wastewater coming in, no industrial inputs to have an issue, and then you can essentially reduce the treated. The last I want to talk about how water energy is a nexus. It goes together. You create energy through hydropower, but it also uses the energy during treatment plant. But now you can give it back, that energy formed in your wastewater by various processes. I'm going to go skip some of the slides and go only 4 or 5 because I do have a little amount of time left. Electrical energy, nowadays there's a lot of work happening, especially in Europe, Israel, and US, or maybe in Australia to an extent, that formation of microbial fuel cell. Essentially, we are saying you're using microbes that are using energy through your carbon and as a source, and nitrate and nitrite. They're also creating some energy. Why can't we produce the energy so it won't be a day far away that you put some grid on top of your aeration system and then generate that energy that can be utilized within the treatment plant. Another one is the biogas. Generate from primary treatment, use this primary sedimentation, digestion, pressure reliefs to thermal hydrolysis, use higher amount of energy, or use combination thereof between fog, that is food, oil, and grease waste coming from industry, coming from various hoteliers, various restaurants. mix with your sludge and use that as a high energy product and create an energy for it. This is just a slide showing the same thought process. This is the fog data that's happening right now in some of the places. And this can oxidize. I'm going to quick with this slide, so don't jump on me. I'm just going to find a slide that I want to talk about. Was thinking is okay. And essentially, this is a diagram I'd like you to focus on. This is called a Sankey diagram, developed by Zubang in 2018. Essentially, what it's talk about how the product phosphorus, nitrogen, and carbon can be used and can be reproduced to use it for a variety of options. Essentially, you can have the phosphorus going into what is called as true white. If you use a digestion process correctly and then use a true whiting process, if you operated the plant, I'm one of the class 1 operator, plant operator certified. So I've operated both water and wastewater plant. If you go and digester, and if you open a flange close to the digester, you would see magnesium sulfate combination with phosphorus in it. It's a true white. It's a yellowish, dark, brownish mixed material that is like a rock at times. So you literally have to take a chisel and a hammer to take it out. So essentially that 35% is going here in that particular system. Then instead of that, you could use that and form a true white separately as an agriculture product and use for phosphorus. Or you can use it for irrigation through nitrogen, and you can use it for residual biosolids for recycling, and how the carbon is being used and so forth. So enhancement of soil, enhancement of solids through digestion. DC Wasa, the next slide I'm going to show it to you, is the largest thermal hydrolysis process plant where it takes up the entire wastewater coming into DC Washington or Washington DC and use the THP to hydrolyze the cells and get more energy. But you can also get what is called as Class A sludge. And Class A sludge is pathogen-free sludge, which is USA EPA Part 503 regulation. And essentially, that is a virus-free, pathogen-free sludge. You can put your hand into it, and it's like a small powder, dried. Then you can use that for soil amendment and things like that. The Okla plant, the 564,000 meter cube per day plant, will generate Class A sludge because it will have combination of thermophilic and mesophilic digestion and also air drying system. So that's another way to look at it. I think I talked about. Lastly, and about 5 minutes I could finish, is essentially you now need to look at it, the recycle reuse of wastewater. And I've done a lot of work on it. Essentially, it's my passion on reuse and providing reuse of different. But technologically wise, I can tell you that absolutely you have all the technology available at your resource. But what is not there is you need to have a public participation. You need to have a public outreach program, because technologically you can achieve high quality water, but psychologically it should be fitting into your mind that, hey, I'm using a wastewater, treated high quality wastewater for drinking or non-potable application. In reality, we all use treated wastewater. Somebody else's wastewater flows into the river, comes through a certain amount of time and being used for a treatment process. But thinking wise, we need to look at it. If you look at it, India and variety of other places are thinking that after 2050, they may not have sufficient amount of water. So we need to start looking at how to conserve the water, how to use this water. We will have sufficient water if we apply it properly and use it wisely by recycling and reusing it for a variety of applications. What I would like to talk always about, as against the fresh water, which is on the left-hand side, the recycled water is a captive resource for that city, captive resource for that state. It has no allocation issue, because if Karnataka is downstream and Maharashtra is upstream, then the issue of water allocation comes into picture. At least in terms of India, the water is a state subject. So it's not a centrally driven subject. So now what happens is that the allocations and systems are derived, both combinations from center and state. If a state, particularly which is upstream, stops water from a river, then there will be disputes. Classic example is Kaveri River. Karnataka doesn't allow to go to Chennai or Tamil Nadu. Tamil Nadu says there is an issue, you need to draw more or send more Kaveri water downstream. But wastewater, which is highly treated and reused, has no interstate dispute. What problem is there other than all that is public perception, awareness, and giving public a full data of what's out there, what's the reality. the moment and time you give full data, full disclosure of the information, I think public will be much more interested in using the reused water and recycled water. What wanted to be done is to create a brand name for your reused water. A lot of people talk, you might have also heard that Singapore uses recycled water, gives them a bottle and so forth. I was fortunate to work on that project also. What's out there is their prime minister or their senior stood up and said, look, don't get water from Johor Bahru, which is from Malaysia. We'll have no choice but to use this water. And if that is the case, we will have to disclose all the details. We drink this water together. They're not doing it directly to potable. There are only a few countries that are doing directly potable. What they did is treated high quality, put it into a reservoir, take that reservoir with a certain residence time, and then use it for a further treatment. What I call that reservoir is I call nothing but a psychological barrier reservoir. That changes the mindset. That needs to happen. There's only one plant in the world which literally used from a house store to sewerage to treatment plant and to house tap is Namibia. Namibia has no water. If they don't do this, they have no water. Very low rainfall, very low. So it comes from literally, I think Babak is doing that project or has completed and operating the plant. There are some plants in US which are coming up very effectively now for indirect potable called as IPR. You take the water, put it upstream into your reservoirs, put it upstream into your river and bring it down. Or DPR, direct potable reuse. That's also happening nowadays. There's a lot of discussions and effective. If anybody's interested, you can go to EPA's website or type IPR, DPR or IPR/DPR. There is a water resource reuse website. A lot of work has been done on, and essentially what everybody's talking about, again, the same old story. 3 barriers, multiple barrier approach, physical, chemical, microbiological. If we meet all these 3, I think we can create a brand. We can create a brand that people will like and so forth. Essentially, this is the steps. Irrigation, you can use secondary. Tertiary, you can use filtered, you can use, and the cost goes up and your direct recovery cost goes down. But this is where we need to be to safeguard the water more and more essentially. Lastly, I would say, I think a couple more slides left. There are a lot of slides underneath here, but I've kind of cut that down. We need to look at the 3 sustainable approaches for freshwater resource management, be it water, be it wastewater. Continue to do RO, seawater desalination wherever it is needed. Continue to do recycle, reuse, and then create measures for R&D into private and public institutions on water and energy, development of FO, that is forward osmosis, and hybrid RO systems that you can develop. You can develop aquifer storage and recovery, basically treat the wastewater, generate a geotechnical analysis, conduct a geotechnical analysis on a confined aquifer, which is dry right now, put water back into it and use it back whenever you use it. And with that, I think I'm done. So thank you very much for the opportunity. Here's the contact information. I think my email is slightly not visible. Let me put that back in different color so you can see. Hello? I'm done.
Okay, sir.
Yes.
Sir.
Okay, let me just share my contact. Here's my contact. I put it in. So first name Uday at njsei.com, and the company email address is njsei.com. And yeah, I hold the post of MD CEO, but I also get into a lot of technical work. I'm also a team leader and designer for this large-scale wastewater plant, the 564, as well as some of the projects in Bangalore. So I've got multiple hats to wear. I know time is short, so thank you for the opportunity and keep everybody safe. And I think I'm ready for questions.
Thank you so much, sir. So now I request participants, those who have any questions, please raise your hand.
I'm going to close this.
Yes, sir. So we have the question from Mr. Lalit. So can you please unmute yourself and continue with your question, Mr. Lalit?
Yeah, good morning. This is Lalit Bazare, Managing Director, Nixie Engineers Private Limited. Thanks a lot for the opportunity to speak up. Dr. Kelkar, thanks for your wonderful presentation. Gained a lot. Just to let you know, We have also worked on the new water plant in Singapore, which is reusing that water. In 2003, I was also engaged the commissioning of one of the new water plants at Seletar in Singapore. Anyway,
I see.
We would definitely like to visit the 144 MLD installation, which is quite amazing. I believe it is MBBR.
Yeah,
And
MBBR followed by membrane ultrafiltration.
Oh, okay. And to be honest, to share with you, we don't have a good experience with MBR systems, and I have visited a number of MBR systems which are underperforming or not performing at all in India, which is a different matter. What I would like to I would like to get to you is we are also working and in this field for last 15-20 years, and we have developed a system with the United Nations guidance, and we are focused on decentralized wastewater plants. Like your 144 MLD plant may require huge space, power, and funds as well. And what we are trying to promote is go for decentralized wastewater plants where 5 KLD, 10 KLD, 20 KLD installations are feasible with less requirement of space, less requirement of funds, less requirements of power. So in that regard, we have also installed around 50 installations in India, and one of them is at a public toilet in Sangamner. It was a government project. So we would also like to get associated with you and with the esteemed organizations like Bharati Vidyapit. So I would definitely like to know your views on decentralized plants, and would like to also know how we could get associated. Thanks.
Sure. Thanks for your question. Honestly, let me clarify one thing, and then I'll give you my input on decentral plants. First of all, 144 MLD Agra is not a wastewater plant; it's a water plant. But it's been operated. It's been operated first as an MBBR, and that's why after MBBR we had a membrane filtration. We could have used regular sand filtration, but we wanted to have a firm physical barrier like a 0.04 micron, so that nothing will pass through. That's the reason. So it's a water plant. Upfront is a wastewater being treated for Yamuna. Number one. Number two, yes, depending upon the location, depending upon the need, there certainly needs to be a decentralized wastewater plant. And there is a lot of input information worldwide available on various decentralized plants. For example, presently under the Japanese bank funded project, we are doing several decentralized plants in Bangalore for the 110 villages that are being brought into the BBMP area, or Brihat Bangalore Mahanagarpalika area, which are under Bangalore Water Supply and Sewerage Board. So decentralized is an option. It's like one size doesn't fit all. Depends upon the area, depends upon the need, and depends upon the systems that you have. Decentralized becomes very effective. Especially if you have area, like say a area where there's nothing sewerage nearby, but there is a space available, you can certainly put a quick decentralized plant at the location and reuse that water for other applications. So yes, decentralized is a there and being used, very much so.
Yeah, thank you, Dr. Sab, and we would. I have noted your email ID. Me and my colleagues would definitely try and reach out to you. At the same time, I would like to ask the organizers, basically Bharati Vidyapit, if we have an opportunity to work with you, and how would we do that?
Yes, sir. Thank you very much that you are interested. I request Soni ma'am to please answer him.
Yes, sir.
Any question can be asked?
Sir, thanks a lot for showing the interest. I think you can drop a mail to me or to Professor Uday on this mail ID of the my personal mail ID, which is given on the brochure also, and we can go ahead with the work which may be a good industry institute interaction. Thank you.
Yeah. Thank you. Thanks a lot.
Thank you so
Yeah,
much,
we
sir.
would definitely.
So we have one more question from YouTube chat where we are streaming live with our today's session. So Mr. Nagraj Sitaram, he has two questions for you, sir. The first question is, he wants to know what are the future drinking water contaminants, both microbiological and chemical. And the second question that he has is how you place the role of nanomaterials in water and sewage treatment process.
I think there is some disturbance, but I'm still
Yes,
going to
sir.
answer it. I think the contaminant list is typically generated by each country, each regulatory perspective.
Sir, can you please unmute yourself and continue with your answer?
Can you
Please
hear me?
unmute. Yes, sir. Yes, sir. Please continue.
So essentially, the contaminant list is typically developed by the regulators for each country, each states, or the cities. For example, in US, there are a lot of issues are happening with respect to finer plastics. There are issues happening with respect to contaminants as NDMA or anything else, or final organic and organomolecular compounds, which is not out here in other parts of the world. So it's kind of difficult to say which contaminant will pop up and which contaminant will be regulated. Obviously, if there is a contaminant list given, then there will be researchers like yourself or ourselves or everybody, including academia, will run around and develop different type of combination of treatment processes using the standard oxidants and so forth. The second one is the nanoparticles. There is a lot of work is currently being done using nanotechnology for both water and wastewater, and it is very encouraging, and it's being used for development in terms of oxidation, development in terms of adsorption, development in terms of sedimentation, and so forth. So certainly, nanotechnology will be there and will enhance the existing processes to a future extent.
Okay. Thank you so much, sir. We have one more question from Mr. Akshay. What is your opinion about the fecal sludge treatment? Is there any firm technology available?
Fecal sludge treatment, especially if you say in the rural areas or areas where there is no transport of wastewater, there is not a single technology, honestly. It's a combination. There are several out there, and I don't want to give exact names because then it will look like I'm promoting somebody over the other. But there is a lot of data available from European countries. There is a lot of data available from World Bank on fecal sludge management, on fecal sludge analysis. There is a data available from Ministry of Urban Development, Housing and Urban Development. I think last week only they just published some guidance, which I have a copy that talks about fecal sludge management and fecal sludge management regulatory systems and what needs to be done with one over the other. I think they are working with GIZ, that is the German arm of financing, and also European I'm talking about Indian perspective that they have. So it's out there. You can have, or if you don't have, just send me an email and I'll send you a copy of that fecal sludge management data and information that has been put out by the Ministry of Housing and Urban Development, Government of India.
Yeah. Okay. Thank you so much, sir. Sir, can I request you to please close the presentation which you have shared so that we can proceed with the vote of thanks.
Done.
Yeah, thank you so much, sir. Now I request Dr. Vidula Sohni ma'am, Head of Civil Department, Bharati Vidyapit College of Engineering, Pune, to please deliver the vote of thanks for the today's session.
Thank you, Priya. Can you hear me?
Yes, ma'am.
Yes. On behalf of Bharati Vidyapit Deemed University College of Engineering, Department of Civil Engineering, and on behalf of SB Patil College of Engineering, Department of Civil Engineering, I thank Dr. Uday Kelkar sir for giving a very lucid and informative speech, which was very informative due to the slides and overall presentation. In detail, he has given us all the details about the various water treatment processes, including lake stratification, different types of aerators, active flow process, membrane process, desalination, reverse osmosis. In between, he has added a good videos of various sites that he has visited from USA, Australia, and other sites also. Related to wastewater treatment also, he has given us the various applications of ozone related to wastewater, as well as not only the technical part, he has also covered the energy efficiency and the cost effectiveness of each and every method. Thanks a lot, sir, for giving such a lucid and descriptive presentation with very good video, and I am really sure that all the participants must be very happy looking at your presentation and looking at your dissemination of the knowledge. Thanks a lot once again. I thank Dr. Uday Kelkar once again. I thank Dr. Praveen Nemade, Principal, SB Patil College of Engineering, for remaining present for this session, as well as all the participants who have attended this session. Thank you, sir.
Thank you very much. Thank you very much for the opportunity.
Thank you so much. Thank you, everyone. The participants are requested, please fill up the feedback form. The link is already sent to you yesterday. Link will be open from 12:30 p.m. to 3 p.m. So kindly fill up the feedback form immediately after the session.
Thank you,
so
sir.
let's declare the session is concluded.
Yes.
Thank you so much.
Thank you, sir.
Madam, shall I conclude the meeting? Soni madam.